In this video, we're diving into a hands-on guide to vector databases, what they are, why they matter for AI applications, and how to use them to power semantic search and retrieval-augmented generation. No fluff, just real practical implementation using OpenAI, FAISS, and Pinecone. Let's get started. A vector database stores and queries high-dimensional vectors, numerical representations of text, images, or audio generated by machine learning models. Unlike traditional databases that match exact values, Vector DBs retrieve data based on semantic similarity. This is key when working with LLMs or AI that needs to understand meaning. Vector DBs use approximate nearest neighbor, algorithms like HNSW or IVF to find the closest vectors quickly. But that speed comes with a trade-off. You may lose a little accuracy for massive performance gains. Also, be mindful of distance metrics, cosine similarity versus Euclidean distance, and choose what your embedding model was optimized for. Let's walk through building a mini semantic search engine using OpenAI and FAISS. So, first, we're going to use the OpenAI library to generate embeddings. We import OpenAI, create a client, and then call the embeddings endpoint with our input text, like vector databases make semantic search powerful. We're using the text embedding 3 small model here. The embedding is then extracted from the response data. Next, we need to store our embedding in a vector database. So, we import FAISS and NumPy, create an index using index flat L2 with the length of the embedding, and then add our embedding to the index. Just a quick note. Index flat L2 is brute force and accurate, but honestly it's not scalable. For larger datasets, you should use HNSW or IVF. Now, when we want to search, we generate an embedding for our query, like, how do I build semantic search, using the same model? We then search the index with this query vector, asking for, say, 5 nearest neighbors. This gives us the distances and the indices of the most similar vectors. Alright, so here we have our metadata dictionary. It's got an entry with 0 as the key, and inside there's a title called Semantic Search Basics and a URL pointing to https://yourdomain.com/doc1. Now, when we run print metadata 00, we're basically fetching and displaying the metadata for our first search result. FAISS is really great for local experimentation, but, when you need to scale up, it's better to use a managed vector database like Pinecone. So, let's walk through some Pinecone code. First, we import Pinecone, then we create a Pinecone client with our API key. After that, we connect to our index, which we've named yourIndex. For upserting, we call the upsert method with a tuple containing media group, hands-on keyboard with code window showing function call, close-up of Python upsert method in IDE, developer writing tuple encode at stock at distribute _equally, doc1, the embedding, and some metadata. Here it's just a text saying vector search is amazing. And finally, for querying, we use the query method, passing in our embedding, asking for the top 3 results, and including the metadata. It's pretty straightforward once you get the hang of it. In retrieval-augmented generation pipelines, vector databases fetch relevant context for a large language model based on user input embeddings. This keeps prompts grounded and responses factual. Retrieval-augmented generation reduces hallucinations and, honestly, it scales really well with constantly updating knowledge bases. Before deploying, just, keep these tips in mind. Check vector dimensions. Normalize if you're using cosine similarity. Tune approximate nearest neighbor parameters for recall versus latency. Align the distance metric with your embedding model. And add metadata filters for better precision. Vector databases are the foundation for AI-native applications. Whether you're building search engines, chatbots, or retrieval-augmented generation pipelines, they make high-dimensional similarity queries fast and scalable. Try integrating FAISS for local prototyping and Pinecone for production at scale. And hey, explore LangChain, Weaviate, and Quadrant to round out your stack. Thanks for watching. Want hands-on code, examples, and templates? Just grab the companion notebook from the description below.